Hi, everybody. Welcome back to the video series discussing how to represent solute transport in the BioRT-HBV model. I'm Liz, and this is the third video in the series, and it will be discussing how to actually run the BioRT-HBV model and then looking at some results. So we've talked about in the last video how important the file structure setup is. It's important to be able to run the model that you have this setup in your file folder. You have the place where you've installed the model as the executable. And in that folder, you have an input folder and an output folder. And the input is where you put the watersheds that you're interested in running. And in here, this is showing the sleeper chloride base. This is the one we'll be working with. It represents the Sleepers River watershed. And basically, I've named it chloride base because this is the base case for solute transport that we're going to run. Then you can see all of the files that we need in this input folder, including the ones for BioRT, and then the HBV output that are required to run the BioRT. So with this in mind, let's go ahead and try this out in BioRT-HBV. So I am running on a Mac. And I can just show you that I have in this folder, like you just saw the screenshot of, we have input, sleeper chloride base. This is the one we're going to be running. And again, because I'm running on a Mac, I'm going to do this in my terminal. And it will say, basically, I am located in that folder that you just saw because those are the same things that you saw in the file folder structure. And now to run the model, I want to run the base case. So to run the model, we do .-BioRT, and then we give it the name of the watershed in the input file that we want to run. So this is sleeper_CL_base. And it just did a bunch of things for us. It read all of our input files from the soil.txt. It read the HBV model parameters, the BioRT control parameters that were listed in chem.txt. And then it also basically read the database, does some math here, or it tells us how it's going to do the math, the matrix math. And then it tells us that it started the simulation, which is going to be the warm-up period. And then it succeeded with the warm-up period. Then it started the numerical experiment, and then it completed the numerical experiment successfully. And so this is what it looks like to run BioRT-HBV on a Mac, and it will look similar in Linux as well. So let's take a look at some results. We have the hydrology output first. Because solute transport is the non-reactive transport of solutes, it relies on the hydrology. Basically, it tells us what the water is doing. And so it's really important that we look at the hydrology first and understand what's happening with hydrology, even though this is not an output from BioRT itself, it's an output from HBV, but it is what controls the water movement that BioRT takes into account for doing the solute transport. So we have a plot of discharge on the y-axis and time on the x-axis. And this is for 1 year because we have constant hydrology. We've just repeated the precipitation and the evapotranspiration for as many years in the simulation as the simulation called for. So we have 4 different outputs in the model. We have total discharge, the stream flow, that black line. Then we have discharge from the surface, which is the lightest blue line, the QSF. Then we have shallow zone flow discharge from the shallow zone as the medium blue. And the deepest blue is the deep zone flow. And so with these different parameters, all of the lighter blues and dark blue will sum up to the total discharge. And we can see that based on the fact that the dark blue and the black are pretty close a lot of the time, except during high flows, that this system is base flow dominated. This catchment is base flow dominated. That means that groundwater from the deep zone makes up most of the discharge, except during these high flow times where we have more contribution from the surface and the shallow zone. So this is just a brief understanding of the hydrology. Now let's look at the warm-up period results. So in the warm-up, we had it repeat the hydrology for 5 years, and we kept the precipitation chemistry constant as well for those same 5 years. It is higher than the initial chemistry in that initial conditions file. Basically, we saw it was 2 times 10 to the negative 20th in the last video. And here it's something like 3 times 10 to the negative 6th. And so if we look at the output, we have the hydrology with discharge on the y-axis and time on the x-axis. And this should look exactly like what we just saw, except we now have 5 years of data instead of just the 1. The hydrology is exactly the same. On the lower panel, we have chloride concentration in the different zones, representing the stream, the shallow zone, and the deep zone. And so you can see we have this initial increase with the first few months, within the first few months. And that's a result of the precipitation chemistry input being higher than those initial conditions provided in the initial condition text file. And you can see that eventually it smooths out. We don't have as much change in the concentration in any of the zones through time, other than what happens annually. And so once the chemistry stabilizes, it tells us that the model is ready to be run in experiment mode because we've reached a sort of steady state. It's not going to change until we perturb the system. So let's go ahead and do that. We did the numerical experiment. This was just the warm-up period. And then we had it do the numerical experiment where we injected a smaller amount of a larger amount of chloride on day 7 of the numerical experiment period. So this was run for 10 years. I'm only showing 5 in these plots, but the same hydrology was now run for 10 years. And on day 7, a pulse of chloride was added, and then it was dropped back down to the constant low value. And so you can see, again, hydrology is presented just for reference, but in the lower panel, we have chloride concentrations through time in the different zones. And you can see that first, we see the breakthrough of the chloride in the shallow zone and stream around the same time. So we see that movement of the chloride from the precipitation leaving the system in the stream and the shallow zone. And then it takes a little bit longer to respond in the deep zone. And then with time, the concentrations all decrease. Basically, we put the chloride in, and then it's slowly left the system through the outflow in the discharge. And you can see that the stream chloride mostly matches the deep zone chloride, except with fluctuations towards the shallow zone chloride concentration. So our stream is this salmon colored, and you can see that a lot of times it's pretty similar to the dark deep zone, except when it dips down and more closely approximates the shallow zone flow, or the shallow zone concentrations. And so this is just a brief overview of what the results look like from the BioRT-HBV model when you're doing solute transport. You can now start to test what happens if we change different parameters in the model. And that will be the next video. We'll try modifying some BioRT parameters to get a sense of what's going on in the system. And if you want to think about more about what this means, feel free. Again, I only presented 5 years of data, but you could run this yourself, see what happens after 10 years, and take a look and try to understand what is controlling the different chemistries in the stream and the discharge and how that relates. So thanks for tuning into this video. Be sure to tune into the final video for solute transport to understand how modifying the parameters change the results. Thanks.